Hello, welcome to the NetIQ Learn. Today we are focusing on the second part of the cryptography lecture, the basic integrity and authenticity. What is including? Cryptographic hash functions, different type of cryptographic algorithms, and cryptographic key management. Let me commence with cryptographic hash function. A hash function takes binary data, message, and produces a condensed representation called a hash. As you can see in this image, we send a clear message to a hash function and it then generates a fixed length hash value that is absolutely unique to that given input message. If we even change a single character of the given message, then generated hash value will be completely different from the previous hash value. That hashing is the base of the well-known technology called blockchain as well. The hash is also commonly called a hash value, message digest, or digital fingerprint. Hashing is based on one-way mathematical function that is relatively easy to compute but significantly harder to reverse. Hashing is designed to verify and ensure data integrity and authentication. Cryptographic hash function is applied in many different solutions, including to provide proof of authenticity when it is used with symmetric secret authentication keys such as IP security, IPsec, or routing protocol authentication. To provide authentication by generating one-time and one-way response to challenges in authentication protocols such as the PPP CHAP to provide the message integrity check proof such as those accepted when accessing a secure site using a browser, and to confirm that a downloaded file has not been altered. There are plenty of different web tools available out there so that you can check how a particular hash function is working. We can take an arbitrary length of clear text data to be hashed, then put it through a hash function and it produces a fixed length message digest hash value. HX is relatively easy to compute for any given x, and it is one-way and not reversible. If a hash function is hard to invert, it is considered a one-way hash. Once the hash value is generated based on a clear message and using a hash function, then no one can view the clear message using that hash function and hash value again. It is working only in one direction, clear text to hash value. Hash functions are helpful when ensuring data is not changed or altered accidentally, such as by a communication error. Hash functions cannot be used to guard against deliberate changes. There is no unique identifying information from the sender in the hashing procedure, so anyone can compute a hash for any data as long as they have the correct hash function. Hashing is vulnerable to man-in-the-middle attacks and does not provide security to transmitted data. Two well-known hash functions are MD5 with 128-bit digest and SHA-256 with 256-bit digest. Just take a look at this illustration. Since the clear message is different, the outcomes, the hashes, are different as well. First, we consider integrity with Message Digest 5 or MD5 algorithm. The MD5 algorithm is a hashing algorithm that was developed by Ron Rivers. It is used in a variety of internet applications today. A one-way function that makes it easy to compute a hash from the given input data, but makes it unfeasible to compute input data given only a hash value. The hash value is changed during communication means loss of integrity. Secondly, we consider integrity with Secure Hash Algorithm or SHA. US National Institute of Standards and Technology NIST developed SHA. The algorithm is specified in the Secure Hash Standard SHS. SHA-1, published in 1994, corrected an unpublished flaw in SHA. SHA design is very similar to the MD4 and MD5 hash functions that Ron Rivers developed. SHA-1 algorithm takes a message of fewer than to the power 64 bits in length and produce a 160-bit message digest. SHA-1 is slightly slower than the MD5, but the larger message digest make it more secure against brute force collisions and inversion attacks. NIST published 4 additional hash functions in SHA family, each with a longer digest. SHA 224 bits, SHA 256 bits, SHA 384 bits, and SHA 512 bits. This is a comparison between MD5 and SHA1. Both MD5 and SHA1 are based on MD4. It involves 64 steps for computation in MD5, while it takes 80 steps in SHA1. For the MD5, it must process 128-bit buffer, while SHA1 should process a 160-bit buffer. Since MD5 computation include fewer steps and less process than SHA1, MD5 is way faster than SHA1 but less secure. Now we consider authenticity with Keyed Hash Message Authentication Code or KHMAC. HMAC or KHMAC is a message authentication code MAC that is calculated using a hash function and a secret key. HMACs use an additional secret key as input to the hash function, adding authentication to integrity assurance. Hash functions are the basics of the protection mechanism of HMACs. The output of the hash function now depends on the input data and the secret key both. Authenticity is guaranteed because only the sender and the receiver know the secret key. Only they can compute the digest of an HMAC function. These characteristics defeat man-in-the-middle attacks and provide authentication of the data origin. The cryptographic strength of the HMAC depends on the cryptographic strength of the underlying hash function, size and quality of the key, and size of the hash output length in bits. Cisco technologies use two well-known HMAC functions. Keyed MD5 or HMAC MD5 is based on the MD5 hashing algorithm, and Keyed SHA1 or HMAC SHA1 is based on the SHA1 hashing algorithm. Now let's be clear on how the HMAC is operating. We send the data plus secret key using a hash function and generate the HMAC. And we attach this generated HMAC to the data and send it through the communication method, probably over the internet. And now the receiver receives the data. Then receiver sends the received data plus secret key, which is only known by sender and the receiver, via the same hashing function and generate the new HMAC value. If the newly generated HMAC matches the sent HMAC with the data, then integrity and authenticity has been verified. If they don't match, discard the message. HMAC is using with the Cisco products. Cisco products are hashing for entity authentication, data integrity, and data authenticity purposes. For instance, authentication routing protocol updates, IPsec VPNs use MD5 and SHA1 in HMAC mode to provide packet integrity and authenticity. iOS images downloaded from cisco.com have an MD5 based checksum to check the integrity of downloaded images, and TAC ACS Plus uses an MD5 hash as the key to encrypt the session. Here, when we consider key management, it is about how the secret key using for hashing should be managed. Key management is often considered the most difficult part of designing a crypto system. There are several essential characteristics of key management to consider, including key generation, key verification, key storage, key exchange, and key revocation and destruction. Now let me explain each characteristic. The first one is the key generation. Key generation depends on the cryptographic system that the key is meant to be used. For instance, Caesar chose the key of his cipher and the sender receiver chooses a shared secret key for the original cipher. And modern cryptographic system key generation is usually automated. Then after a key has been generated, we need to check whether that key is weak or vulnerable for an attack to uncover the ciphertext. Almost all cryptographic algorithms have some weak keys that should not be used. For example, cipher, ROT0 and ROT25 considered as weak keys. With the help of key verification procedures, these keys can be regenerated if they occur. Then after the key is generated and verified successfully, we need a way to store that key securely. Modern cryptographic systems store keys in memory. The next challenge in key management is to find a secure method of a key exchange or an untrusted medium. And finally, what do we need to do if a security key is compromised by unauthorized third-party personnel? It involves key revocation and key destructions. Revocation notified all the interested parties that a certain key has been compromised and should no longer be used. Destruction erases all keys in a manner that prevents malicious attackers from recovering them. Two terms that are used to describe keys are key size, the measure in bits, and also called the key length, and key space, the number of possibilities that can be generated by a specific key length. As key lengths increase, key space increases exponentially. For instance, 2 to the power 2 key is equal to a key space of 4. 2 to the power 3 key is equal to a key space of 8. 2 to the power 4 key is equal to a key space of 16, and so on. Adding one bit to a key double the key space. For each bit added to the DES key, the attacker would require twice the amount of time to search the key space. Longer keys are more secure but are also more resource intensive and can affect throughput. This table shows how the key space calculated using key length and the number of possible keys that could be generated. There are mainly 4 types of cryptographic keys, namely symmetric keys, asymmetric keys, digital signatures, and hash keys. Symmetric keys can be exchanged between two routers supporting a VPN, while asymmetric keys that use insecure HTTPS applications, and digital signatures that are used when connecting to a secure website. Hash keys that use in symmetric and asymmetric key generation, digital signatures, and other type of applications. We will discuss all of these in detail in upcoming sessions. Performance is another issue that can influence the choice of a key length. Shorter keys enable faster processing but are less secure, and longer keys equal slower processing but more secure. An administrator must find a good balance between the speed and protective strength of an algorithm. With that, we can conclude today's session. Thank you for watching, and please do subscribe to my channel for the latest update every Monday. Have a wonderful week.